Hello, this is Professor Kuehn. We have been talking about Chapter 10 in A Student's Guide to the Great Physics Texts, Volume 3. This is the work of Hermann Helmholtz on the conservation of force, published in 1847. Let me remind you of what we had discussed in our last lecture. In that lecture, we got up to about page 115. And on this page, we were talking about the concept of kinetic energy. So if we imagine a ceiling, and from the ceiling is suspended a string, on the end of which is located a block of mass m. And if we fire a bullet toward this block, this represents a bullet, it has mass m, and this bullet has an initial velocity v. When it strikes the block swings upward. So before the collision, what I've depicted here is a situation before the collision. The bullet, by virtue of its motion, could do work. So the bullet had the capacity, to accomplish work. And this capacity to accomplish work was by virtue of its motion. How much work could it accomplish? Well, it could accomplish a work equal to 1/2 the mass of the bullet times its velocity squared, and that was called the kinetic energy of the bullet. Remember, the word energy, etymologically, is the work inside, en erg, the work inside of it by virtue of its motion, so it's able to accomplish that work. So then, after striking this block, what's going to happen is this mass is going to swing up like this. It had been down here. And the mass is going to swing upwards to some height. So now the mass is up here. It has been elevated by some height from the original height up to the final height. We'll call this height h. And once again, it had been down here. And it swings upward in this direction. So what I've depicted here is, whereas here was before the collision, here is after the collision. The mass of the bullet and the block eventually come to a state of momentary rest. At a height h. Of course, they're going to swing back downwards after that, but they're elevated by a height h. And now the important thing to keep in mind is that the elevated masses, which are, I guess we could call them big M, and I guess little m is lodged in here too. So here's our little m, which is lodged in there. The elevated masses, capital M and little m, can now, in principle, do work. How could they do work? Well, in falling back down through the height h. So just as in our previous lecture, we talked about whenever you have a mass that's elevated by some height, that mass in falling back down or descending can accomplish work. So the question is, how much work can those do? How much work could these two masses, after having been elevated by height h, how much work could they do? Well, it's just going to be the available work, maybe I'll put it this way, the available work of capital M is given by its mass times g, this is the weight of that, times the height through which it falls, or it could potentially fall. And what is the available work of the little mass? Well, that is its weight, little mg, that's its weight, times the height through which it could fall. In other words, and this is the important point that I'm trying to make, is that the elevated masses are now said to have a potential energy. potential energy. What do we mean by potential energy? Well, it is an ability to do work. It's an ability to do work by virtue of their location, or their configuration. So their location, in this case it's elevated, or the configuration. They are farther away from the center of the Earth than they had been before. So the question naturally arises, how much potential energy does a body or a system of bodies contain? Well, the potential energy they contain is precisely equal to the work that it took to put them into that configuration. So how much potential energy? I'll write PE for potential energy. Precisely the amount of work. The potential energy is equal to the amount of work it took in order to put them into that configuration. Okay, it's however much they have then a potential energy equal to the amount of work that it took to put them into that configuration in the first place. So for example, in the case we're discussing above, the potential energy is said to be a gravitational potential energy. So I'll put a little grav down here, potential energy due to gravitation, and that is just equal to, in our case, it would be the sum of the two masses times g times h. That would be the gravitational potential energy that those two masses have by virtue of being at a height h. Now, that could have been given to them by the bullet hitting the block and swinging up, or it could have been given to them by me simply lifting those two masses up through a height h. Notice that the gravitational potential energy of these elevated blocks can be turned back into kinetic energy, or energy of motion, right? So if, for example, maybe I'll come up here into this corner. I know I'm running out of space, but that's okay. The potential energy of these elevated blocks was just equal to the sum of the two masses, m plus m times gh, and they could swing back downwards and acquire a kinetic energy. This would be at the bottom if they were to swing back downward after having been knocked up high. Well, that would be the kinetic energy at the bottom, which would be m plus m times their velocity squared. That's 1/2 the total mass of that system times the square of the velocity. Notice that this allows us to relate the height that they're located and this velocity that they would have at the bottom. After all, if they have some potential energy at the top, they're able to do work, then they swing back down and that turns into kinetic energy. Then you can write that the potential energy at the top is just going to be equal to the kinetic energy that this two mass system has when it swings to the bottom. And I could write this like m plus m times g times h equals 1/2 times m plus little m v squared. I can cancel out these masses, and I get that the velocity is equal to the square root of 2gh. So this allows us to relate the speed of swinging through the bottom to the height through which they fall in order to gain that speed. So the key concept here is that the energy is really a shorthand way of describing the ability of some body or collection of bodies to do work, either by virtue of its motion, that is, if it has kinetic energy, it can do work by virtue of its motion, or by virtue of its configuration, that is, by lifting masses up to some height, for example, they acquire potential energy, that is an ability to do work. Next time when I lecture, I will talk a little bit more about some other examples of potential energy. Here I'm talking about gravitational potential energy, that is lifting objects through some height, but other kinds of configurations can store potential energy. So next time we'll talk about bending back a crossbow, which stores elastic potential energy, or compressing steam, which also stores a form of elastic potential energy.